to the next second talk in this session. We have with us Dr. Vijayakumar C, Principal Scientist, CSIR-National, Thiruvananthapuram. He received his PhD in chemistry from University of Kerala in 2008. Later, he worked as a postdoctoral research fellow at the Organic Material Group, Graduate School of Engineering, Osaka University, Japan. He joined the Chemical Sciences and Technology divisions of CSIR-National Thiruvananthapuram in 2013. He has been recognized by several awards, including prestigious Ramanujan Fellowship, Kerala State Young Scientist Award, and the Raman Research Fellowship. He has established many collaborations with the high-ranking research institutions such as Osaka University, National Institute for Material Science, Hokkaido University, Japan, ITMO University, Russia, AGH University of Science and Technology, Purdue University, USA. He has been invited to Hokkaido University as a visiting scientist in 2016. He got selected for the microfellowship program of ITMO University, Russia in 2020. He has published more than 50 papers in international journals with 4,000 total citations. His current research interests include halide perovskites, thermoelectric composites, fluorescent materials, supramolecular chemistry, and photochemistry. With this brief introduction, I invite Dr. Vijayakumar Sir to deliver the talk on Bismuth Halide Perovskites. Over to you, sir. Sir, please.
You are muted, or your voice is not audible. You're not muted, but voice is not audible.
So am I audible now?
Yeah,
yes, I am audible.
Okay. So thank you, Chairman, for the nice words of introduction. And first of all, I would like to thank Professor T. Pradeep and Dr. Kavita and Dr. Rajiv Varghese for the invitation. So today I'll be talking to you on Bismuth Halide Perovskites and how we can modulate the optoelectronic properties of these materials by using organic spacer cations. So you already listened to two excellent talks in this area, that is halide or hybrid perovskites on the first day by Professor D.D. Sharma and on second day by Dr. Anshuman Nag. So I hope that you must be aware of the importance of this area. These materials are considered as the wonder material for the next generation optoelectronic devices, particularly for the photovoltaic applications and light emitting diodes, lasers, memory devices, photocatalysis, etc. So there are so many applications. But there are some issues associated with this material. One is the poor stability under ambient conditions, and second is the toxicity of the lead. Okay, because most of the performing materials are lead-based materials, so people are trying to avoid lead-based material in the materials and devices. So the research in halide perovskites moves in different directions, and one of the major direction in this area is the lead-free material. So, and another one is the luminescent perovskite material. Actually, I am working on these two areas. So I will give a brief outline of the work we are carried out in the nanocrystals, luminescent nanocrystals, and later I will discuss in detail about the lead-free materials. Basically, we are working on the bismuth halide perovskites and what we did in this area. So before going to the details of the work, I would like to give a brief introduction to perovskite. And I know you already got some or came to know about some basics of perovskite, but I am giving it in a slightly different way. And this is a plentiful mineral available on the earth crust and especially in Ural Mountains of Russia. And calcium titanate is the first perovskite discovered, and it looks like this. And it was discovered in 1839 by a German mineralogist named Gustav Rose. And he named this material after the fellow Russian mineralogist Lew A. Perovsky. And any material which is having a structure similar to calcium titanate, you can call a perovskite. But later, there are a lot of research happened in this area, and not only material which is having exactly similar structure of calcium titanate, but a different structure, but some similarity here and there even comes under the class of perovskites. So that I will discuss later. And this is the typical structure of a perovskite. It can be represented by the formula AbO3, and this is the rock solid perovskite or the perovskite available in nature. But what I am talking in the later part of my talk is the synthetic material. Those are lead halide perovskite, or generally the halide perovskite materials, and different derivatives of that material. So the naturally available perovskites can be represented by the formula AbO3, and the crystal structure looks like this. And here A is a metal cation like calcium, potassium, sodium, and B is another metal cation like titanium, lead, tin, strontium, bismuth, and O is the oxide anion. So basically, the oxide anions form a octahedral structure like this, and the B metal cation occupy inside the cavity of the octahedron. And several of these octahedron join together through corner sharing, join together to form a three-dimensional structure like this, and it forms a 3D structure and grows in all directions. And the cavity formed by the 3D structure is occupied by the A cation, and it is actually giving structural stability and the charge neutrality to the material. And we can use, as I mentioned, we can use several kinds of metal cations as the A cation, A side cation, or B side cation. And that allows us to make or develop diverse perovskite materials with engineered properties and suitable for tailor-made applications. And depending on which atoms are used in the structure, it can have very impressive properties like magnetic properties, colossal magnetoresistance, ferroelectricity, piezoelectricity, electrical conductivity, ion conductivity, superconductivity, catalytic properties. So you can name any of the properties of material, and most of the properties you can see in a perovskite material, except these perovskite oxides are not semiconducting in nature. Okay, and because of these properties, we can use these materials for sensors, capacitors, electro-optical switches, electrode materials, memory devices, fuel cells, catalysts. Okay, but as I said, these are not semiconductors, and they cannot be used for the photovoltaic application. But later, there is another class of related class of material was developed. Purely synthetic material was developed in mostly by Professor H.L. Wells in 1890s, and this is having the same perovskite structure, but there is some difference. And here the oxide anions are replaced by halide anions like iodide, chloride, bromide mostly, and this can be represented as AbX3 instead of AbO3. And again, here the X anions are forming a octahedral structure, and the B cation is occupied inside the octahedron like this, and several of these octahedrons are joined together to form a 3D structure, and the free space is occupied by a organic cation or cesium ion. Okay, so that's the difference. In the perovskite oxide, it is occupied by another metal ion, but here it is mostly organic cations. We don't have much choices because the cavity is really small, so you can use only small cations like methyl ammonium or formamidinium. But of course, if you want to use, or if you want to make a all inorganic halide perovskite, there is a possibility of using cesium. That ionic radii is very much suitable for the cavity generated by these octahedrons. So these three cations can be generally used to produce three-dimensional AbX3 type halide perovskites. And as I said, the synthesis was happened mostly, means basic structures were made in 1890s, but nobody was considering this material as useful material for applications. And later, Professor David Mitzi from Duke University in 1990s, he did a very extensive optoelectronic characterization of these materials. And again, there was not much takers for this material because people didn't find much applications with this material. But interestingly, by 2005, Miyazaki and co-workers found that it can be used for DSSC application. But again, stability was a major issue with these materials. And in 2009, Professor Park and Professor Greatsell found that these materials can be used as a whole transport material in DSSC application, and they developed the DSSCs with 9% photo conversion efficiency. Later, this area exploded because people realized that these materials having a lucky combination of unique optical and electronic properties together with very cost-effective processing. So this actually created a perovskite revolution in the last decade, and there are many groups currently working on this material, and they found that this is one of the most promising materials for the optoelectronic applications, particularly solar cells, light-emitting diodes, sensors, and photodetectors. And majority of the groups are focused on the solar cell applications of this material, and there are another groups, several groups working on the light emitting devices and other applications like photodetectors, memories, sensors, lasers. There are many groups working on lead-free perovskites and several groups working on luminescent perovskite nanocrystals. So our interest is on these two areas. We are chemists, basically chemists, and we try to develop lead-free perovskite, and that is the main topic of today's lecture. And we are also working on luminescent perovskite nanocrystals. These are obviously lead-based materials. So before going to the main topic of the today's lecture, I just want to show what is happening in our laboratory on perovskite nanocrystals. Why these materials are important? Because these are the three reasons summarized here. They show very high photoluminescence quantum yield, typically about 90%. You can get nearly 100% in many cases. And the emission colors can be easily tuned across the visible region by simply changing the halide anion. That is very easy, chemically very easy. And you can get a very, very high color purity, like the full width at half maximum can be as low as 12 nanometer. And we developed several perovskite nanocrystals, mostly with methyl ammonium and formamidinium cations, organic cations, and we made several shapes and materials with different shapes and aspect ratio, as you can see here. And they show excellent stability in most of the organic solvents, except in high polar solvents like DMF and DMSO, and they show very good stability even if we dip it in water compared to the 3D perovskite. The 3D perovskite can decompose within few seconds, but our material can survive for several hours. And the film quality is very, very good, which is important for the device applications. And we did extensive studies of these materials in the area of how they behave when we excite this material, and what are the properties like excitation energy migration in these materials, and electron transfer of from this material to suitable acceptors like fullerenes. And we done an extensive study, and we realized that these materials in the film state can show very efficient diffusion of charge carriers. Generally, the excitation energy migration, either in the excitons are moving, or in some cases, these excitons are separated into charge carriers and they are moving. And it is possible to restrict this diffusion of the charge carriers as well as the excitation energy migration by doping these films with fullerenes or fullerene derivative. And efficient electron transfer is possible from the perovskite nanocrystals to the fullerene derivative. And we we published this work in 2017 in Angewandte Chemie and in Nanoscale in 2019. So interested people can read those papers. And these materials are showing efficient excitation energy migration and electron transfer, just like natural photosynthetic systems. So we try to understand what is the excitation energy transfer in this material to suitable donors. So energy transfer and how these materials can act as light harvesting antenna. And we found that they can be show very, very good light harvesting antenna properties, and it can nearly completely transfer the excitation energy to suitable dye molecules, and it can show superquenching phenomenon. And not only that, they can act as both as energy donor as well as energy acceptors. And when we incorporate these materials with the suitable emitting polymer matrices, we can even prevent the halide ion migration. This is one of the major issue in this perovskite material, because they can show halide ion migration and the properties will go bad with under excitation of light. And we can actually prevent the excitation and this halide ion migration in these systems, and we can generate very efficient white luminescent materials out of this. And we published this work in Advanced Optical Materials in this year. And we have also developed visibly opaque and near infrared transmitting material. These are useful for the night photography applications as well as for the security application. We have incorporated square-in dyes with this material by generating iodide ion vacancy in this material, and by incorporating the square-in dye molecules into this perovskite matrix, we were able to get a opaqueness up to 742 nanometer. That means this material can completely absorb the entire visible spectrum. But at the same time, we can get a nearly 90% of transmittance in the Nair region. So this is very much suitable as a visibly opaque near infrared transmitting material. Again, we published this last year in Advanced Optical Materials. And several of our nanocrystals are suitable for making non-volatile memory devices. And we found that the iodide ion vacancy in these materials playing a key role, and the switching is basically depending on the migration of these iodide ion vacancies from one electrode to another. And we developed several high-performance, air-stable, non-volatile memory devices, of course, with the help of collaborators. My collaborator in IIST, they made the devices. We are basically chemistry people. And we made these devices under solution processing under ambient conditions. And it is possible to tune the entire memory properties using chemically modifying the structure by adding chloride ion to the material. It is possible to switch the set and reset voltages. And the next major thing in this area is using this material for the neuromorphic application. That is an area coming up right now. We don't have expertise in this area, so our group collaborated with a group in Poland under the Indo-Poland project, and they are working on the device part, and we are working on the material side currently. So now coming to the main topic of today's lecture, that is lead-free. That, as I said, we are currently working on Bismuth Halide Perovskites, and you can see this is the major metals used for developing perovskite. That is, lead is the major one, and we can use tin or germanium because it belongs to the same group. Similarly, we can use bismuth and antimony, and we can also develop double perovskite by using indium and silver. We can also use cesium as the A-side cation and chloride bromide ion as the iodide as the anion. So as you can see, this lead, methyl ammonium lead iodide, that is a mostly explored material, which is having a band gap of 1.5. Now, since the lead is very toxic and poisonous, people are looking for other metal cation, and tin is the first choice. And you can make a tin-based perovskite with even with a much lower band gap. But the problem associated with tin is that it can easily undergo oxidation from SN2+ state to SN4+ state, and that is not suitable for most of the applications. So that is the issue with tin. And germanium, because of some issue with the germanium, the band gap cannot be reduced much lower. So most of the germanium-based materials are showing very high band gap like this. And another obvious choice for replacing lead is bismuth, because bismuth is first major reason is that bismuth is generally considered as a non-toxic metal, and an adult can tolerate up to 15 grams of bismuth, and it is one of the highly abundant heavy elements present in Earth. Up to 2 × 10⁻⁵ (8% of the Earth crust is bismuth. And most importantly, this Bi3+ is isoelectronic with Pb2+. You can see the molecular weight is 82 and bismuth is 83. So bismuth 3+ is isoelectronic with lead 2+, and which is having a similar NS2 lone pair of electrons, just like lead. And this NS2, presence of NS2 electron was found to be the major reason for most of the optoelectronic properties of lead. So bismuth is also having the same NS2 electron. So that is why we selected bismuth as a possible choice of replacing lead, and we decided to study this bismuth halide perovskite and see what are the possibilities. And the literature says that this bismuth can form a variety of structures because it has this possibility to form different oxidation state, and also it has capability to form stable complexes with many organic cations. And because of that, you can actually use bigger organic cations forming zero-dimensional perovskite like structure. We cannot say it is a real perovskite structure because it is a deviation from the ABX3 stoichiometry. So we call it as perovskite derivatives or perovskite-like material. So they can form a zero-dimensional perovskite-like material, or in with other derivatives or other moieties, it can form a 2D perovskite structure, or it can even form a perovskite double perovskite structure with cations like silver or rudolphite-like structures. So there is a variety of structures are possible with bismuth halide and bismuth metal. But the present issues of perovskites are means bismuth halide materials are summarized here. So far, most of the bismuth halide perovskite reported consists of electronically inactive organic cation, just like methyl ammonium or formamidinium. They are electronically inactive and they cannot contribute to the overall electronic properties of the materials. And in addition to that, these are forming low-dimensional crystal structures, and because of the low-dimensional nature, there is a strong quantum confinement effect in these materials. And since they are using insulating organic cations, these charge carriers are confined at the inorganic bismuth iodide clusters. They cannot move to the electrodes. So these are not really suitable for the photovoltaic application. And another important aspect of bismuth halide perovskite is the significant electron phonon coupling, and because of that, this excitation energy can be easily transferred to the lattice movement, and that will kill the radiative energy, or the radiative decay will not happen. The non-radiative decay is promoted, and because of that, the charge carrier lifetime will be very, very low. And since again, due to the formation of the low-dimensional material, there is no much connectivity between the inorganic units. And not only that, the organic cations cannot contribute to the band edges of the material, and because of that, these materials are having wide optical band gap. And another issue is the weak polarizability of the organic cation, and they cannot screen the Coulombic interaction between the electron hole pairs. And because of that, high exciton binding energy is observed in this material. So we are trying to address these issues, how we can try to address these issues, whether it is possible to address this issue. And we selected a few organic cations to develop bismuth halide perovskite and see how it is performing in the perovskite structure. First, we try to understand the quantum confinement in this material, and because of the high quantum confinement in this material, they show very high exciton binding energy and low charge carrier dissociation. So we made the most common methyl ammonium bismuth iodide, and you can see a strongly quantum confinement structure in this material. You can see the yellow one is the inert atmosphere created by the methyl ammonium. So there is no continuity electronic coupling is possible between the inorganic clusters, and that is yielding a very inferior optoelectronic properties in this material. Of course, it is difficult to go to 3D structures with the bismuth halide materials. So what about making quantum well structures? So if you cannot get good properties from the quantum dot structures, go to the quantum well structures, because that is much better than the quantum dot structures. So we try to remove the, or we try to avoid the methyl ammonium cation, and instead of that, we used a dication, a propyl diammonium cation. So we can use less number of organic cation, because here one organic cation having two charges. So you statistically need half of the organic cation required, and we synthesized the bismuth halide material like this, and here we found that the edges of the octahedron is shared in the material, and they formed a very beautiful quantum well structure as we anticipated, because by using less number of the organic cation, actually one side of the three-dimensional structure is not containing the organic cation. So you can see only this direction is having the organic cation, but along the inorganic cation, there is no hindrance created by the organic cation. So the charge carriers can easily hop along that direction from one inorganic octahedron to the neighboring octahedron very easily. So because of, and in addition to that, the distance between the octahedron is very small, 4.5 angstrom. And because of that, the charge hopping is very easy in this material, and we were able to develop relatively efficient photo detector devices with our material. And interestingly, we didn't need to use any hole or electron transport layers, because our material itself is transporting the charges. And we try to understand the next. We try to understand the dielectric confinement in this materials, and this dielectric constant of the inorganic and inorganic wells and the organic barriers are huge. That mismatch is huge because the organic components are not polarizable, and inorganic units are having charges, or it is polarizable, and because of the dielectric constant mismatch, these materials show huge dielectric confinement in their properties. And because this dielectric confinement is directly proportional to the exciton binding energy, the exciton binding energy is very high in this material, and the charge carrier separation is very, very difficult in this material. But so it is not suitable for the photovoltaic application. So if we can use polarizable organic cations, this organic cations can screen this electrostatic interaction between the charge carriers or the excitons very effectively, and that can reduce the exciton binding energy. So that was the basic idea, and this was actually not our idea. In 2018, it is already proved in lead-based perovskite material. Professor he and co-workers, they used the ethanolamine and 2-phenyl ethyl ammonium cations, and the ethanolamine is having a very good polarizability, and the other one doesn't having a good polarizability. So when phenyl ethyl ammonium was used, the polarizability of this material is low, and because of that, binding energy is above 300 electron volt. But on the other hand, when they used a polarizable organic cation, the binding energy was extremely low, very even lesser than 5 electron volt. So that was inspiring to us, and we developed materials by using a benzyl ammonium cation. It is reasonably polarizable compared to methyl ammonium. So this is our material. The top one is our material, which is giving very nice crystals and with a nice scattering. And the lower one is the standard material. We made that material for comparison. And the interesting thing is that this material actually showing a preferential orientation along the 0-20 plane, which is actually controlled by the packing of the organic cation. So normally in most of the perovskite, the packing of the material in the film state is controlled by the inorganic octahedron. But in our material, this organic plays a key role, that is acting as a template and control the film formation direction. And we found that in our material, the exciton binding energy is much lower than the standard material. And because of that, our material showed a 2.5-fold enhancement in the microwave conductivity. So that is basically the intrinsic conductivity of the material measured in the nanometer scale. So our material is showing very good conductivity compared to the methyl ammonium, the standard material. And so we can say that the exciton separation efficiency is very low in the standard material, but it is very high, relatively higher in our material because of the polarizability of the organic cation. So that can assist the exciton separation in our material. So that is our finding. And the next thing, we try to understand the electronic band structures. So as I said, most of the perovskite material, including the lead-based material using this non-semiconducting material or insulating organic materials for making the perovskite structure. So they do not contribute anything to band structure or anything to the overall optoelectronic properties of the material. So, but if you can incorporate some semiconducting organic cation to the perovskite structure, it is possible to get contribution from the organic cations also, because the studies by Mitzi revealed that there is a possibility of 4 kinds of band structure. One is the type 1A, where the organic components are contributing to the both conduction band and the valence band maximum. The other one is the type 1B, where the inorganic structures are contributing to the both conduction band and the valence band of the material. And normally most of the perovskite comes to this class, that is the type 1B band structure. And type 2A, here the organic is contributing to the conduction band minimum, and inorganic moiety is contributing to the valence band maximum, and vice versa is happening in the type 2B. So if you are using an electronically inactive organic cation, you will end up with a type 1B band alignment. And we found that if you are using an electronically active organic cation, you can get a type 2A band alignment. And it was proved by making 3 materials. We made 3 bismuth halide perovskite having biphenyl cation, that is the first one. And second and third are the naphthalene derivative. This is naphthalene diamine, and this is naphthalene monoimide, and this is diimide. And you can see there is no contribution from the organic component in the total density of state from the in the first material. This actually my friend in IIT Indore did the calculation, the theory calculation, and they found that a type 1B alignment in the material with the biphenyl cation, and there is no proper pi stacking in the biphenyl cation, that again detrimental to the overall charge carrier mobility of the material. But in this second and third cases, they not only form the type 2A band alignment, that is the organic components are contributing to the band alignment, but in addition to that, they are forming a very stable self-assembled structure. So this can easily transport the charge carriers along one direction. So that is very, very important for the device application. And because of that, these materials containing the naphthalene imides showing very good conductivity. Again, the time to solve microwave conductivity analysis we did. And the one-dimensional structures we developed showing a very good anisotropy along the crystal axis. And not only that, the charge carrier lifetime of one of our material is very high, 18 microseconds, which is significantly higher than the well-known methyl ammonium lead iodide, as well as several lead-free perovskite, lead-free double perovskites. And in the case of optical band gap, as I initially said, the major drawback of the bismuth halide perovskite is that their wide optical band gap, which is about 2 electron volt, and it is mainly associated with the low dimensional crystal structure. And this optical band gap is basically influenced by the distortion of the organic framework. If the distortion is very high, the metal and halide orbitals will have poor overlapping, and that will lead to a huge optical band gap. And the other one is the chemical pressure exerted by the organic cation. So if you use bigger organic cation, they can exert chemical pressure. If it can be negative or positive, it can be either compression, and that normally gives a narrowing of the band gap. And in the case of it is a expansion, that will lead to a widening of the band gap. So organic cations having low lying, what we observed that the organic cations having low lying pi star atomic orbitals could reduce the optical band gap by additional energy level contribution at the band gap energy states. And we proved this by using 4 of our materials, and there is a clear trend of extending the visible light absorption of this material to a longer wavelength by using the self-assembling or the semiconducting in organic components. And we were able to get a band gap as low as 1.8 electron volt, which is much higher than most of the reported bismuth halide perovskite reported in literature. Those are represented by the blue one, and our materials are the red one. And of course, there is a drawback of association of including bulkier semiconducting cations in the structure of bismuth material, because it can completely destroy the inorganic framework. So the future research direction should be focused on designing templating functional organic cations. So they should be able to template the inorganic packing, inorganic octahedra packing, and which could provide better electronic dimensionality to the inorganic framework. And coming to the last 2-3 slides, I can summarize the advantages of the bismuth halide perovskite materials we developed and other materials developed by other groups compared to other lead-free perovskite. One is they exhibit a diverse inorganic framework connectivity compared to other lead-free materials like tin-based and double perovskite, which provide extra handles to tune the optical band gap without varying the halide anions. And due to the strong interoctahedral electronic coupling, they feature a narrow optical band gap compared to similar dimensional double perovskite. And in addition to that, unlike the double perovskite, these materials are generally direct bandgap materials. That is an advantage, which makes them ideal for optoelectronic applications because of the strong visible light absorption. And most importantly, these bismuth-based material demonstrate superior chemical stability compared to the lead-free tin-based material under ambient conditions. And these materials can be used for, of course, several applications, but of course, it is not suitable for the single junction solar cell devices because they are giving very poor efficiency of 3% alone, but it can be used along with other materials to make tandem solar cell or indoor photovoltaic application, because the band gap is very suitable for this application because it is having a band gap of nearly 2 electron volt. And besides the photovoltaic application, it can be used for the photo detectors, catalyst, and X-ray radiation detectors. And unlike the lead halide perovskite, these special structured bismuth halide perovskite could be employed as photocatalyst in aqueous mediated photocatalytic reaction for the carbon dioxide reduction, hydrogen production, and dye degradation. And they can also be used for X-ray absorption, as X-ray sensors, because they show very good X-ray absorption coefficient because it belongs to the heavy element category. So in summary, a deep understanding is required of the role of functional organic cation on the optoelectronic properties of bismuth halide perovskite for the tailor-made applications. And the further research should be focused on developing bismuth halide with the various semiconducting organic cations. We already proved that they are very good for improving the optoelectronic properties, and we can look at molecules like pyrrhizinium, imidazolium, or violegens. They may be good candidates. And in addition to that, we can use charge transfer complexes, incorporate charge transfer complexes into the perovskite structure, and they would yield very good visible light absorption. And hopefully, we can make bismuth halide perovskite which are environment friendly and high efficiently for higher efficiency for the electronic device application. So finally, I thank to my students, Dr. Chinnadure and Dr. John Paul did most of the work I showed here, and my collaborators. And this is my group. And finally, I thank the funding agencies like CSIR and DST and Kerala State Council. And finally, thank you all for your kind attention. Thank you all.
Thank you, sir. We move on to discussion. Participants, if you have any question, please unmute and ask. Sir, I have one question.
Yeah, please.
What is the stability of this type of compounds in photocatalytic application?
So, so far the literature report says that they show good stability. unlike most of the lead-based material. But we haven't done anything in the photocatalytic application, so I don't have any first-hand experience. But literature report says that they are good.
Okay, sir. Okay, thank you. Thank you, sir, for your wonderful talk. As a token of our love and gratitude, we have a small memento for you, sir.
Thank you.
We will send it to you by post.
Yeah.
Thank you,
Thank
sir.
you all.
Thank so
Yeah,
much.
thank you all for listening.
Once again, I would like to thank Jiamping Z and Dr. Vijayakumar C for your nice talk. Thank you. Thank you.